Welcome and study with Tanzania Institute of Education.
Hello, welcome to our chemistry class. My name is Madam Jennifer Kaislege. I'll be with you discussing Form 3 topic concerning with volumetric analysis. And today we are going to proceed where we have ended, but we'll be discussing about standard volumetric apparatus. Standard volumetric apparatus, these are apparatus used in volumetric analysis. And they are most used during experiment in titration process. Then before we discuss the titration process, let us see what are those apparatus used. In standard volumetric apparatus are apparatus used in volumetric analysis. These are pipettes. We must have a burette. We must have a retort stand. We must have a thirster funnel. We must have the measuring cylinder. Reagent bottles. And the bottle of indicator. So this is the apparatus that you're going to use during volumetric analysis experiment. But before we see how do we use them, we need to know what is the standard solution. There are some terms that is used in volumetric analysis, and these include standard solution. Standard solution. Standard solution. The question is, what is standard solution? The question is, what is standard solution? By definition, standard solution is a solution with known concentration. A solution with known concentration, or a solution whereby the concentration of it is well known. So, by definition, a standard solution is the solution with known concentration. Reminding ourselves about the meaning of concentration, we said we have two types of concentration. We have what we call mass concentration, and we have what we call molar concentration. So mass concentration, it is the concentration measured in gram per cubic decimeter, and the molar concentration or molarity, it is a concentration measured in mole per cubic decimeter. Therefore, a solution with known concentration, whether it is in gram per cubic decimeter or moles per cubic decimeter, is what we call a standard solution. For example, 10 gram of potassium hydroxide solution in 1 cubic decimeters of a solution. This is a standard solution. Why do we call it a standard solution? Because from this data we have, 10 gram of potassium hydroxide dissolved in 1 cubic decimeter of a solution can give us a concentration. And so we know that after having the concentration, which is 10 gram in a cubic decimeter, 10 gram dissolved in cubic decimeter, we have the mass concentration of potassium hydroxide. Then from the mass concentration, remember we know how to calculate the molar mass of potassium hydroxide, which is molar mass of potassium hydroxide. What is the mass of potassium hydroxide? It is 39. Then what is the mass of oxygen? It is 16. What is the mass of hydrogen? It is 1. So it is 39 plus 16, which makes, this is 1 plus 9, 10 plus 3 makes 40. This is 16 makes 56 grams per mole. 56 grams per mole. So that is the molar mass of potassium hydroxide. And also we have the concentration, which is given by the mass given over the volume, which makes 10 gram per decimeter cubic, which makes 10 gram per decimeter cubic. Therefore, from there, I can say that molarity of potassium hydroxide is given by concentration measured in a gram per cubic decimeters divided by the molar mass. Divided by the molar mass. The molar mass is measured in a gram per mole. So from there, we get the concentration of potassium hydroxide. That is why we call it a standard solution. Then after understanding a standard solution, what is another term that you can encounter? It is the molar solution. We have another terminology that we need to know. It is known as the molar solution. And then the question is, class, what is the molar solution? Molar solution. Molar solution. These are the most important terms because you're going to be meeting with them during titration process. So a molar solution, we can define it as a solution which contain 1 mole of a solute, 1 mole of a solute dissolved in a liter of solvent, liter of solution. That is molar solution. That is molar solution. A solution which contains 1 mole of a solute dissolved in a liter of a solution, that is the molar solution. So this is what we call molar solution. We can define it as the solution which contains 1 mole of a solute dissolved in a liter of solvent. Then after understanding these terms, we have another thing that we need to know. What are these? We need to know what we call titration. So what is titration? And then what is acid-base titration? What is titration and what is acid-base titration? Titration is a process of adding one solution to another until the reaction ends or until the reaction is at complete. That is the meaning of titration. So, is the process of adding one solution to another solution until the reaction complete. So in chemistry, we are dealing with the acid and base titration. Among of them, one must be a standard solution. If acid is going to be a standard solution, then a base must be a solution with unknown concentration. Therefore, that standard solution will be used to determine the unknown concentration of the base. But if the base is a standard solution, that means acid will be a solution with unknown concentration. Therefore, we'll be using the standard dissolution, which is a base, to determine the concentration of acid, which is unknown. Therefore, what is acid-base titration? Acid-base titration is the process of adding acid slowly to the base until indicator changes or until end point is reached. So we are adding acid to a base with the assistance of indicator, and then when the reaction is at complete, there will be the color change, so that we say it is an end point. And from there, we say that that is the neutral point. Why? Acid-base titration is the same as neutralization reaction. Why is it a neutralization reaction? Because there is a formation of salty and water. Refer to salty in the previous topic. Therefore, when you talk about a neutralization reaction, there must be the formation of salty and water. For example, if I have example, consider the following reaction. There is potassium hydroxide. This is a base. I'm going to titrate it with the acid, for instance, hydrochloric acid. There must be dilute. So when these two reactants meet, there will be formation of the product. And what is the product? We must get potassium chloride and water. Potassium chloride and water. This is neutralization reaction because there is a formation of water molecule. If you recall the ionic equation, you are going to find that after cancelling the spectator's ion, it is going to remain only water, while in the reactant side, you are going to remain with the hydroxide and hydrogen ion. That is why we say it is a neutralization reaction. Therefore, during titration, acid and base, one of it must be a standard dissolution, another one must be a solution with unknown concentration. So when they are reacting together with the help of indicator, when we reach the end point, that is a neutral point, there must be a change in color. And then what is a choice of indicator? Why do you need to use a certain indicator in a certain reaction? When we are titrating acid and base, we must have indicators. And in chemistry, we have only three indicators. Only three indicators. One, it is methyl orange. Another one, it is phenolphthalein. Another one is litmus paper. So the common indicators we have, we have litmus paper, we have methyl orange, is abbreviated as MO. We have phenolphthalein, abbreviated as P or P, not a plaster of Paris, but phenolphthalein as indicator. Therefore, in titration, we are only using either methyl orange or phenolphthalein, but not litmus paper. The question is why? Litmus paper, it is used to identify whether the solution is under acidic medium or under basic medium. But it cannot be used in titration process because it is not going to change and give us the actual value. Therefore, that is why litmus paper is not recommended or is not used during titration. But if I have two solutions and I want to identify which one is an acid, which one is a base, I will use litmus paper. But when it comes to titration, I'm going to use either methyl orange or phenolphthalein depending with the strength of acid and base. Therefore, let's see the choice of indicator. Choice of indicators. What makes you to use methyl orange? What makes you to use phenolphthalein? It depends with the strength of a base and an acid. Therefore, if I'm going to use strong acid versus strong base, here, any indicator, you can use either methyl orange or you can use phenolphthalein, depending with your choice. Any indicator is favorable. Any indicator is used. So it depends. If methyl orange is easier for you, use it. If phenolphthalein is easy, use it. For a case of strong acid and a strong base, someone will ask, Madam, can I know an example of a strong acid and a strong base? For instance, if I'm titrating potassium hydroxide, it is a base, versus sulfuric acid, or sodium hydroxide versus hydrochloric acid, or versus nitric acid. This is what we call the strong acid. This is what we call a strong base. So in case you are titrating among of these, choose any indicator, whether methyl orange or phenolphthalein. But what if I'm titrating the strong base versus weak acid? What if I'm titrating strong base versus weak acid? Weak acid. What is the favorable indicator? It is phenolphthalein. POP, phenolphthalein. So this is the favorable indicator for a case of the reaction between strong base versus weak acid. Strong base versus weak acid, use phenolphthalein. What is example of the weak acid? For example, if I'm titrating sodium hydroxide versus acetic acid. Acetic acid, it is CH3COOH. That is acetic acid. Or if you are using carbonic acid. So the favorable indicator will be phenolphthalein. The question is, why phenolphthalein? We are using phenolphthalein because phenolphthalein is acidic in nature. And since it is acidic in nature, it determines the hydroxide present within the base. That is why it is a favorable indicator used in case you are titrating weak acid versus strong base. But what if I'm titrating weak base versus strong acid? What is the favorable indicator? The answer will be methyl orange. Or MO. Methyl orange is a favorable indicator for a reaction between the weak base versus strong acid. For example, if I'm titrating ammonium hydroxide, it is a weak base, versus sulfuric acid, I must use methyl orange. Ammonium hydroxide is a weak base, and the sulfuric acid is a strong acid. In case I'm titrating those reactants, I must use methyl orange as an indicator. Another question is, what if base is weak, and acid is weak? What should I use? So, in case you are titrating weak acid versus weak base, there is no satisfactory indicator. No satisfactory indicator. So you cannot learn this reaction because there will be no endpoint, because there is no satisfactory indicator. So we are using indicator in case we have weak acid, strong base, strong acid, weak base, or strong. Both of them are they are very strong. That is the choice of indicator you must use during titration process. Now we have discussed about the choice of indicator. We need to know how can we record the data in the lab after experiment. But before I show you how do we record the data, we need to know what the formula that I'm going to use to calculate the unknown concentration. If one concentration is known, we call it molar ratio formula. This formula is applied when one component is missing, 5 components is given. So let us derive the formula and see how we can apply the formula to calculate the unknown concentration. Remember I told you, if acid is a standard solution, base must be a solution with unknown concentration. So how can I determine the concentration of the base? The concentration unknown. So let's derive this formula, which is going to be the basic formula we are going to use whenever we meet a question concerning with concentration unknown. We need to determine unknown concentration. Or if you want to determine the molar mass of a given compound, or if you want to determine the percentage purity within a compound, or if you want to determine the rate of crystallization, this will be the basic formula to start with. So consider two solutions. Consider two solutions A and B. A and B. The number of moles in solution A is Na, and in solution B is Nb. Now how do we relate molarity and number of moles? Refer to the previous discussion. We said molarity is equal to number of moles over volume. So molarity is abbreviated as capital M is equal to number of moles over volume. Make subject N. So N is equal to molarity times the volume. Now if I'm looking the number of moles for A, solution A, while I have the molarity of solution A and the volume of solution A, what will be the equation? So for solution A, number of moles will be given by molarity of A times the volume of A. Call it the first equation. For solution B, number of moles for B will be equal to molarity of B times the volume of B. Call it the second equation. Then find the ratio between number of moles for solution A and B. If you are looking for the ratios, I will divide the number of moles for solution A over number of moles for solution B. Therefore, Na over Nb will be equal to molarity of A, volume of A, divided by molarity of B, volume of B. This is our equation. Make sure you are equating the formulas to relate. So if this is A, they must stay in one side. And for B, they must stay in another side. So what are we going to do? Cross multiplication. That is molarity of A, volume of A, number of moles of B is equal to molarity of B, volume of B, number of moles of A. I want A to remain in one side, and I want B to be in the same side. So what I'm going to do, I'll divide by Na and B both sides, Na and B. Cancel the one which relate. So this and this will give me 1. This and this will give me 1. So what remains? It is molarity of A, volume of A over number of moles of A equals to molarity of B, volume of B over number of moles of B. What is this? This is called the molar ratio formula. Molar ratio formula. So this is the formula, and it will be used when one component is known, another one one component is missing, the rest are known. Where do I get an A and an B? They are obtained from the balanced chemical equation. On the reactant side, the coefficient number on the reactant side is the number of moles for A and number of moles for B. MA, VA, and NA belong to acid. This is molarity of acid, volume of acid, number of moles of acid. Molarity of base, volume of base, number of moles of base. Therefore, Na will be the coefficient number along the base, and the Na will be the coefficient number along the acid on the reactant side. Now we have the molar ratio formula. Let me construct a table of results. I have already titrated acid and base. I got the result, which I'm going to use to find this concentration unknown. So, table of result. Table of result after titration. So you'll draw your table, and this table will contain experiment, and then so we must have a pilot as a starting point, experiment 1, experiment 2, and then experiment 3. So the first one, it is known as final volume. Final volume. The last one you read after titration process, when you reach the end point, it must be in cubic centimeter. Then you must have initial, where you have started. Initial volume in cubic centimeter. The last one, it is volume of first used. Volume used. Also in cubic centimeters. So when you record the data, you'll be starting with the initial, going to final. So to get the volume of first used or the volume used, you must take the final minus the initial. You'll be getting the volume used. Therefore, for today, we have seen the different terminology you're going to use during titration. What is titration? What is the choice of indicator? What is acid-base titration by definition? What are the apparatus used in volumetric analysis? And also, we have seen the choice of indicator depending with the strength of acid and base. But also, we have derived the molar ratio formula that you're going to apply during examples, different examples and the different questions. Therefore, for today, let me end here. I hope you have enjoyed my subject. Let me meet with you the other time. My name is Madam Jennifer. Goodbye.